we've got quite a bit of stuff to do over the next couple days, and I want to ensure that we land prepared for that nifty thing happening on Monday. So, to that end, this is what I'm giving you. You're going to probably hate me because it's not what you want, but it should be enough to get us going. Are they like rabbits instead of goldfish? Is what this? I love those. Oh,
like every 4 to 5 minutes.
They're like, oh, you want some goldfish? I'm like, what?
Yeah.
Goldfish? What the hell? That's disgusting.
Did anybody not get one? Right, so guys, I'm going to go over that in a minute. So I need your focus. All right. So based on the homework that's due on Friday, don't forget it's due Friday, not Monday, right? So, and it's a very short assignment. Are there any questions on that you want to cover? Yes.
The last problem, it's like super conceptual.
It is like super conceptual, meaning really Jesus.
Yeah, it's like when we go over it,
Basically, what you got is if we map wavelength versus sort of ability to see, so to speak. I forgot what they call that axis. What we find out is that in the range of visible light, we've got something that our cones can see, and then we've got the rod. And this all ends up being around the red end, and then this is what you get at the other end. So basically, this is cones, this is rods. So our eyes have both kinds. I've told you a little bit which of these two is favored by us in terms of looking at things. So, which of those is the thing that we used to look with? When I mean, standing here, I can see students sitting on the side of the room and that side of the room, but if I want to look at them, I turn and there's a part of my eye I actually look with. Even though when I look at you, I'm aware of everything else in the room. The part that I look with, what kind of nerves? Cones. Everybody with me on that? Cones. Because cones, they contain all the color information. All right? Rods are more kind of black and white kind of thing. I mean, that's not entirely true because we can see they certainly cover the other spectrum, but they're more sensitive to other things. Rods are, in fact, most sensitive to motion. When I was in the Navy, one of the things they used to tell us is that when it's really dark at night and you can't, there's not enough light for you to see with your cones, if you're searching for another ship on the ocean, if you just look, you're in trouble. But if you sweep your eyes, that'll cause any lights that are on the horizon to have motion with them, and your rods will pick them right up. All right? So that whenever you're in a situation where you're looking for something that's dim, don't just stare. Like if you're doing astronomy, you're looking at the sky trying to find a dim star, like a comet, or the comets that show up and they're faint. If you stare, your chances of finding it are very small. But if you, don't do this, but just kind of focus and sweep your eyes. And if there's any faint light there that moves when you turn your head, your rods will pick it up. And then once you find it, you'll see it to look at. Did they tell you anything like that? Did they still teach? You were never on a ship. Now you were in the Navy.
Yes.
That's kind of weird. All right.
Why were you in the Navy?
Because why would I have not been in the Navy?
What were you doing in the Navy?
This is a different question for a different. I am so old that everybody was required to enlist for military service.
Oh.
And you could choose. If you didn't do anything, they put you in the Army. I chose the Navy.
Good choice.
I like the ocean. So, yeah, that actually was an excellent choice, but that's a different story for a different day. And I got out there with no tattoos, figure that out. All right, so coming back to this thing, guys. What we're learning here is that they both are about equally sensitive on the red end of things, but as you get to the purple high energy end, the short wavelength, then the rods kick in. So rods are easier to see dim light at the high energy end. But the cones are what we typically see with it all day. This one's really hard for us to do in the classroom because you'll tend to hit your neighbor in the face. But I'm going to have you try to do this, and if it works, good. If it doesn't, if people yell at you, you can quit. So the idea is that if you, how I'll start is this: I look straight forward, and I just kind of move my hand to the edge here, and then very slowly just move them back and forth until they just disappear out of sight. Once I find the place where when I'm looking straight forward I don't see them, then wiggle your fingers and your hands will show back up. All right, so you can do it with just one hand. So just look straight forward, And you kind of want to move slow because, of course, we can pick up the motion otherwise. But get your hand to where when you look straight forward, you don't see it. And when after you get just to that point, then when you wiggle your fingers, it should pop back into view. All right? And that is because what your rods don't do the looking, but they see it. So as soon as you wiggle it, your rods pick up the motion, and that expression we have of seeing something out the corner of your eye is very real. Why do you think our eyes have evolved to do that?
Predators.
Because we're the only animal where both eyes point forward. All the other animals are here, so they already have side vision. So we needed something to catch, to see if things from the side were coming at us. And so our rods developed to be able to detect very faint motion at the edges. All right. So, like I say, if you just look straight forward, as soon as I do that, I see literally out the corner of my eye, I can see the motion. So when you're not in front of everybody and you're afraid of hitting faces, try that at home, and you should be able to pick up on that. So does that help understand the point of the question? I don't remember the exact things they were asking.
Yes.
All right, but
So all they're trying to say.
so red, they both are pretty.
Axis, I think that was a logarithmic.
Yeah, it is logarithmic because because the range of what we see and the range of what we hear is really wide.
Okay.
So it has to do with the intensity of
So it being higher than the tones, what does that mean?
Yeah, it means that it's more sensitive to see it. But the irony is that it's not something that both things are happening at once. Even though the rods are more sensitive, they're not what you look for.
Okay.
Now the other thing is that what we have in our eyes is something called the fovea centralis, which is the part, as I told you before, where we bundle up all the nerves and take them out in one location. Excuse me, that's the blind spot. The fovea centralis is the place in the eye where the cones are most dense. So that when you look at something, that's the part of your eye that you turn and put that, so you've got a high density of nerves there. When you look, you're trying to form the image on that part of really high density. What's intriguing to me in all of this is that literally, if you're in your textbook and you look carefully, you can look from one side of the period to the other. You can almost feel your eye shift. If you look at the little dot and you focus on the left side or you focus on the right, you can feel your eyes shift that tiny angle. That's how precise that location is in terms of what we look. What finally limits my ability to see detail? What about my eyes finally says, okay, smaller than this you're not going to see? It's actually a word that we've been studying, but you probably didn't realize that that has anything to do with it. So in lab on Monday, did you pass laser light through round circles? Yeah. Did you get a chance to do that? Pass laser light through one of the round holes? What did you see? Like I had a tiny hole. When the laser light goes through a tiny hole, did it make a tiny dot? No, it made a big smudgy circle surrounded by other circles, didn't it? That's due to what? There's only one circle, one hole, and you have a sudden pattern. So it's not interference because there's only one. It's diffraction. All lenses are inherently diffraction limited because what happens since they make images spread out, it's like the same thing if you drive on a highway at night and you look and see a car way far in the distance, do you see two headlights? No, you see one. Why? There are two headlights.
No, that's the diffraction one.
Diffraction limited. In other words, the resolution of the lens, even a perfect lens, is going to still not give you perfect images because it's going to be diffraction limited. Why do you only see one light when it's really far away? Because it's a pinpoint of light and another pinpoint of light right next to it, and they both make smudgy circles that overlap, and you only see one circle on your retina. Do you understand what I'm saying? Is that it's close, I see two circles. But as it gets further away, the angle becomes smaller, and these circles that are made by diffraction overlap. And so if I have one here, and I have one here, we can sort of see a little dip. So what we would actually see is something that looked like this. And at that point we say we've resolved it. We can tell it must be two objects. But if it gets any closer, it just sort of looks like that. And I really can't tell if it's an oblong object or what. So when I can no longer see that there are two things, then that's because of diffraction. If I get a telescope, then I can put it on there and then I can resolve it back to two again. All right? So it turns out you can get different resolution, but we have a circular opening on our eye, which makes everything have sort of a spread out image. what limits the detail that my eye can see is when the images, like the dot on the eye and the top of the letter I in a print, if their images overlap and I can no longer see them clearly, then I'm past the resolution of my eye. Now there's other stuff that can go on. You can have cataracts, you can have other things. But even a perfectly shaped lens in your eye under perfectly lit conditions will have a limit to what it can see because of diffraction. All right, so see that, and I had some of you do this, and I do this mostly to make you embarrassed, but that's all cool. So what you can do is look at a light source, and this is kind of hard to explain, but what I want you to do is I rest both my thumb and my index finger on the third finger there, and what I do is I hold it up to my eye, holding it really close. I'm not trying to look at my fingers, I'm trying to look at the distance, and typically a light is a good thing. And when I look at the light, I gradually allow my thumb to approach my forefinger, and long before they touch, I will see a sudden series of parallel lines jump from my finger to my thumb because the diffraction from the edges of my finger begin to overlap. It's quite interesting to see. So you hold it right here and just gradually bring your thumb and your forefinger together, being very slow so they don't actually touch. And before they touch, you should see some kind of weird stuff happen.
Looks like.
You should see kind of a bending, and the way I see this, there's a sudden bunch of parallel lines and it looks like my thumb reaches up to touch my forefinger even though I can feel that they're not actually doing that. So you're too far from your eye. You literally want it so close to your eye that your fingers aren't in focus. You can still see it?
No.
Okay, no, you need to get it so close to your eye that you can't really detect, that they both look blurry. And then when you do that, you'll get a real clear picture of diffraction taking place. That's what limits the kind of detail you can see. So if you're too embarrassed to do that in class, remember what I said, go home and try it. All right? Did anybody come in who didn't get a copy of the practice sheet? I think that's just one. If it's two, you have to study twice as hard. All right, so now, so any other questions on the homework that's due on Friday before I move on? Yes?
Problem 24.
Give me just an idea of what it is.
Let's see, it is, by what angle should the second polarized sheet be rotated relative to the first to reduce the transmitted intensity of 1 beam?
All right. So I'm going to tell you that the reason you got the answer before that right is for a wrong reason. And you've joined a big crowd of people who made the same mistake. All right? So you've got lots of good company. And the other good news is it's really easy once you see what to do. So what happens is we've got two filters lined up, all right? And so if they're lined up, the first one polarizes it, and the second one, it's already polarized in that direction, so no further change in intensity takes place. In real life, is that what happens? No, because real filters always have a bit of, it's going to cut it down. We're not modeling this. So I've got this like this. Now I'm going to rotate the second filter until the intensity that comes through is 1/2 of what the first filter. So through the first filter is always 1/2, right? When unpolarized light lands. So what I'm saying for the second one is I want the intensity, which is given by the law of Malus, right? I want this to equal 1/2 I naught. So this is a restriction. Make the transmitted intensity half of what we started with, but the law of Malus says it ought to be this. Right? So when I look at this, that's just, what they're asking me is this, is make sure that cosine squared theta equals 1/2. So what you do is to solve this for cosine theta, you take the square root of both sides, and then take the arc cosine of this side, and it'll give you 45. Now, for the next question, all that changes is instead of 1/2, you put 1/8. And then, so the trick is take the square root of it, and then take the arc cosine to get the angle. Does that make sense? Everybody good with that? Yes. So the first one says do 1/2. The problem a lot of people are doing is we started with maybe we started with them at 90. I don't remember, but in any case, they tell you at 90 it's 0. Here it's 100%. So where do I get 1/2? And you say, well, 1/2 of 90 is 45, and it happens to work, but for a wrong reason. So when they ask about 1/8, they're going to get it wrong. So the trick is this. When they say they want to cut down by 1/2, you do this whole step. If they said 1/17, you'd still do this. You'd say cosine squared theta equals 1/17. Then you would take the square root of both sides, and it would say cosine theta equals the square root of what, this is 1/2, but it could be 1/17, it could be anything. Now take the arc cosine of this side to get theta. All right, is everybody good with that? Okay. Any other on that homework set that you have a question? Yes, go ahead.
24 and 42.
All right, so again, I just need a little bit of heads up with that.
Two polarizing sheets are oriented at an angle of 20 degrees relative to each other.
All right, so I already know where that one's going. So I just need, I've been helping so many people today. I've got these problems memorized. So, and this is one with 10 degrees.
Yeah.
Yeah, I mean, everybody had different numbers, but basically it's this. So this one's hard to visualize if you just try to do this equation. So the basic thing is as follows. We've got, in your case, it's 20 degrees. I'm going to say that I've got one filter oriented such that its transmission axis is along the x-axis here. All right, this doesn't really matter. I just need, and the other one you said is 20, right? So then I've got another one whose orientation is 20 degrees away from that. So there's two filters there. Is everybody with me? So I've got one filter that's this way, actually this. One filter this way, one filter this way. All right. Then, after we do that, they tell me light is coming in polarized at 10 degrees from each of those. So it's halfway in the middle. All right, so it's 10 degrees here, and it's 10 degrees here. So the light's coming in like this. So when it gets here, the first filter that it's going to hit, I don't care which it is. It's not going to matter. I can use this one or this one. What's the angle between the light and the x-axis? I've got it polarized at this angle right here. So if I'm polarized here, what's the angle between the polarized light and the axis here? 20 is from here to here. I'm halfway. It's 10. Everybody see that? Tariq? That's a puzzled look, so I need you to talk to me. Let me do this. Here. I've got one filter like this. I've got one filter like this, and I'm going to call this theta. Light's coming in at theta over 2. All right? So I don't care which filter you're putting in front. I really don't care. When I come in, no matter which one it is, I am theta over 2 away from it. In this case, it was 20 and 10. Some people had 80 and 40. Everybody had different angles.
Okay.
But so when the light's coming in polarized, halfway in between, the first filter it hits, no matter which one it is that half angle. So it's going to be 10 degrees in this case, or whatever angle you had. It's going to be 10 degrees for that. So you're going to use I naught cosine squared 10. And now you've got the intensity through the first one. What's the angle? Once it's done, and I was using this one, once it's done, when it goes through a filter, the light that emerges is polarized along the axis of the filter. So now it's here. What's the angle between that and the second filter?
20.
20. Because it's the full thing. Don't use 10. Even though it was 10 and 10, that's not what's happened. Once it goes to the first filter, now it's polarized this way, and the other filter is 20 degrees away. So you're going to use 10 for the first one and 20 for the second one.
So polarization is always happening.
It only happens at the filter you're on.
Right.
All right, so it's not smart. Once it's gone through that filter, it doesn't know it exists, and it goes to the second filter. Sean, I need you to talk to me a little because I can see you're not happy.
So it's asking for the intensity.
Right. So we know that the intensity when it hits the first filter is some I naught. When it goes to the first filter, it's going to be whatever that I naught is times cosine squared 10. That gives me through the first filter. Whatever number that is my new intensity, and I multiply by cosine squared 20 to find out the amount that gets through the second filter.
I guess I'm having a hard time wrapping around the setup that you.
All right, so let's go ahead and just write this out. So let's say that I naught is the polarized light coming in. All right? How much makes it through the first filter? Well, I is equal to I naught cosine squared 10. I'm going to call that I1. That's how much makes it through the first filter. How much makes it through the second filter? What's my intensity that hits the second filter? I1. So it's I1 cosine squared 20. If I write that all the way out, it's I naught cosine squared 10 times cosine squared 20. This is the amount that's reduced. Because that's my initial. So those two multiplied together is the factor by which I've reduced the intensity. Yeah.
For cosine 20, it's 20 because they're going.
It's 20 because what happens, if this is 10, and this is 10, and this is my polarized light, when it hits this filter I use 10.
Yeah.
But this is 20 away from that one. So when I hit the second filter, it's 20 degrees.
Okay.
In other words, it's really stupid. You almost have to think this. When the light hits the first filter, I mean, here it is, the first filter is 10 degrees away. Now it's polarized this way, and it doesn't remember there was another filter. It's just light polarized this way, and that one's 20 degrees away. Or 40, or whatever your numbers were in the problem that you did. Everybody had different numbers.
So when a light hits the screen, polarization always happens along the transmissions.
Polarization is always along the transmission axis, the TA, the theta TA. When it emerges from that screen, that is the direction of polarization.
So for I1 is equal to I naught cosine squared 1. Why is it that in the end answer we don't even consider I1? We just have I naught.
Oh, because what this is I1, so this is I1.
Oh, okay. So then what happens to
This is
I1?
I1, I1 cosine squared 20. So I1 from here substitutes that,
Okay.
and it, does that make sense? Okay. Anybody else? Yeah.
Cosine squared in.
Oh, so the way you do that is put the angle in, or put cosine in your angle, hit it, and then square answer. All right. I don't know of another easy way to do that. So do you understand what I'm saying? So on my calculator, I just go cosine, and then I enter 20, and it gives me an answer, and I hit answer square, and I just square my answer.
Or you can put in the parentheses if you want.
Well, yeah, you can put it in parentheses, but don't put it after. The way we write it, we write it this way because this way is confusing. All right, so this is just a standard way we write it. Your calculator doesn't recognize this. So what this stands for is, as Terry correctly points out, you can enter it this way. Put it in parentheses and square your parentheses. The way I do it, if I have it, is I just take cosine squared, whatever my answer is, I just square my answer.
I guess, so it's still, for the first part, it's only asking for an angle of 20. But I can put that answer, it would look like those.
That would be after the second part. That would be part B, right?
Oh. So this is only for cosine.
Right. This is the answer to part B. So the first, you do this one for the first, and you do this one for the second. Right, because the first one's only 10 degrees.
Still not working though.
All right, let me see.
Cosine.
No, cosine 10 is your first answer. Right? Oh, no, you're right, 20. Okay, that's the second. Factor by which intensity is reduced after passing through both sheets. So, all right, so I was remembering the question wrong. So on the first one, they're oriented at 20. Guys, I'm sorry. With the first one, oriented at 20. Unpolarized light passing through a filter always does what? Reduces by 1/2.
Okay.
It's always 1/2 of it. The first passing of unpolarized light through a filter is always reduced by 1/2. So your first one's 1/2. I get confused because in part B they start with polarized light. Part A they don't. So you usually put you do 1/2 times cosine squared of 20.
The intensity.
All right. So let me explain that better. So the first one we have unpolarized light. We have a filter like this and we have a filter like this, which is 20 degrees. If unpolarized light, I don't care what right angle, but unpolarized light goes to the first filter, how much is lost? 1/2 always. All right. If it's unpolarized light hitting a polarizer, 1/2 is always lost. So I get 1/2. Then I get the second filter. Now I use the law of malice and I say, okay, you take that 1/2 the intensity and you multiply the cosine squared of 20. And so the 1/2 cosine squared 20 is the factor by which it's reduced after going through both filters.
Yeah, so 144.
All right, does that make sense? on then part B, they give you a polarized beam, so don't do the factor of 1/2. You have to use because it's already polarized for the second part. Okay. Yeah, sorry, I had forgotten that you gave my polarized out there. So why is light always reduced by 1/2 when it goes through unpolarized light goes through a filter? Why is it always reduced by 1/2?
Some of them get in, some of them don't.
All right. This is a test to see whether or not you actually remember any of your trigonometry. Cosine squared plus sine squared equals 1. Which means that for any value of theta, this is true. And since it always adds up to 1, and these look exactly the same except for offset, they both must have exactly the same average value. And what two average values that are the same add up to 1?
0.5 and 1/2.
So that means the average value of cosine squared is 1/2, and the average value of sine squared is 1/2. The other way to do this, since you have to use this information, and because my brain is full of totally useless things, and we have to share this, is if I have a sine wave, all right, and I now square it, what's the maximum value of sine? What happens when I square it? What's the minimum value? -1. And what happens when I square it? 1. So what happens is that when I square sine, it looks like this. All right? Everything becomes positive, it becomes slightly more rounded. Then I get my hacksaw, and I cut halfway down, and every little top piece drops in and fills the hole. So the average value is 1/2. All right? So that's another way you can think the average value of cosine squared is 1/2. And that is where the law, that law of 1/2 intensity through the first filter comes from, because it's the average value of cosine squared for all the different various ways that can be polarized. Okay. Other questions? Go ahead, you've got more on that one.
Just other problems.
Just like that? No, we've got more. Let's get those figured out.
Yeah, the next one, 2402, which is the 40-watt light bulb.
All right. Keep going, because there's two 40-watt light bulb problems.
40-watt light bulb is 1.7 meters for the screen.
All right.
That should be applied.
So here's the thing. 40 watts by definition is power, right? That's what 40 watts is. It's a rating of power. Intensity, by definition, intensity is the power over the area. When I talk, there's a certain amount of energy, power that's in my voice, and you guys hear me pretty well, but hopefully people in San Francisco don't as I speak right now. But why would they not hear me? Since the power of my voice is not going to change once it's out of my mouth. Why don't they hear me? Because it's spread over a bigger and bigger and bigger area. So the power is still the same, but the intensity is far, far less because it lands over a larger and larger area. It's the same thing. If I have a 100 watt light bulb sitting here on the table, and you're in the room looking at it, and then you go 5 miles down the road, it doesn't change how bright or how much I'm having to pay to have this light on. What changes is the amount of that light that actually hits your eye, because that light has now spread over a much, much larger area. Well, when that light leaves the bulb, what direction does it go?
Everywhere.
Everywhere. And what's the shape of everywhere? Spheres. Does that make sense to everybody? If I have a point source and it goes everywhere, then that energy is landing in the shape of a sphere. So in order to find the intensity, we need to know that it's basically landing on a sphere. And if we find the ratio that goes with that, then we can know the intensity at any moment. So I say, therefore, the intensity for that particular problem is going to equal 40 watts over 4 pi 1.7 meters squared, because I'm 1.7 meters away from the bulb, and all of that light landed on a sphere of radius 1.7. And this allows me to calculate what the intensity is for any distance away from the light bulb. Right? And if you don't realize that 4 pi r squared is the surface area of a sphere, it's standard mensuration formula, but it's something I would give you if you ever needed it.
Oh, that's my umbrella? Oh, sorry.
Go ahead. All right, so hopefully you don't need it. All right, so y'all understand the intensity then is basically just depending on how far away from the light source I am. All right, So in both that and the next problem, they're going to invoke that idea of the intensity, and you need to use that 4 pi r squared to go where you're going with that. Yeah.
Going back to the example of sound, is it the reason that you can actually, if a normal voice can't hear from several hundred feet distance, but if someone is in a narrow tube, you can hear through the tube because of that, with a small area?
Have you ever tried that? You can hear it, but you don't understand it at all. The standing waves that get set up actually make that incredibly horrible to listen to, but you can hear it. Yeah, because it basically it's echoing. Instead of spreading, it's echoing, and the sound does go down the tube. Yeah. I talked about this briefly before, but again, why is it in the old movies, if you ever watch old movies, when the cowboys would put their ear to the train tracks to see if the train that they were going to rob of all their gold was going to come in? Is that just a movie thing, the putting your ear on the train tracks?
The vibration to the solid
No, what was the reason I gave you?
certain area.
It's because the speed of sound in iron is so much faster that it can travel a much greater distance before it basically dissipates. All right. So yeah, that's a little bit different. Right? So you're traveling through a different medium. So right there. Have you ever had the experience of getting up in the morning and fog has rolled in, and even though you can't see, you can hear things you normally wouldn't hear? That's because the moisture in the air makes the speed of sound much faster, and so sound can get to you relatively more quickly. So we hear things we wouldn't normally hear because of the higher speed of sound. The speed of sound is basically measured on how hard is it to squish something. So which is easier to squish, air or water? Which is easier to squish?
Air, you're not squishing.
Well, what I mean is, if I were going to compress it, if I had it in a container, I wanted to compress it, I can compress air. Can you compress water?
No.
No. So that means that water is hard to compress, therefore sound's going to travel faster in water, so a lot of fog and moisture in the air speeds up sound.
So the harder something is to compress,
The faster sound is. So that's why iron in the railroad, the sound travels really fast. The problem with the rain is making its own noise, which hides things. So that, I mean, it would be, but we don't hear it because of the actual noise of the rain. All right, so that all aside, before we get too far off topic, I'm not trying to rush you. Are there any other questions on that last bit? So, on the test, one law of malice application, right? You can expect one law of malice application. All right. In fact, it's not going to be very complicated because we really didn't have very many problems on it. So it's just going to be some very simple, straightforward application of the law of malice, which is what? I not cosine squared theta. Where theta is what? The angle between the polarization and the transmission axis of the polarizer. If there's only one polarizer, just 1/2. Okay, good. If there's only one polarizer, then just going through one filter, we just get 1/2 of the original intensity.
So if we add layer of polarized film, it's just going to be one of another.
So to make the practice that, what I want to do is I want to do the following. I have unpolarized light passing through a filter oriented like this, and then through a subsequent filter oriented like this. So I have theta TA1, theta TA2. So how much of the original light goes through the first filter? Half. How much goes through the second filter?
1/4.
Okay, Polly, talk to me.
You don't know what everybody else is thinking about. And you ask like, what is the next?
All right, I've got light.
Uh-huh.
It hits this filter. How much makes it through the first filter? Half. Now that light hits this filter. How much makes it through?